So in this video, I'm going to talk about some more modern versions of TCP, TCP Reno and NewReno, where TCP Tahoe solved the congestion control problem such that TCP could operate, the internet could work again. It wasn't necessarily as high performance as it could be, in the sense it was a bit more conservative than it needed to be. And so since then, there have been improvements to TCP, although still keeping the original mechanisms of TCP Tahoe, to make it, to have it send data more quickly and have higher performance. So I'm going to walk through two of those additions. One is something called in TCP Reno and then TCP NewReno. So recall for TCP Tahoe, if the protocol is running and you encounter a timeout or a triple duplicate ACK, which implies that there's a lost packet, you do three things. You set your slow start threshold to be the congestion window divided by 2. So it's determining when you're going to enter the congestion avoidance state as the congestion window grows again. You set the congestion window to 1, and you enter the slow start state. The idea here is that you're sending along, you're sending data. Let's just say here is the window size. You're sending data, something happens, there's an event. You set your threshold to be half of your original window size. You set your congestion window to be 1. You enter slow start again, exponential growth. And then when you reach this threshold, you do additive increase again. So that's TCP Tahoe's behavior. And so here's a picture just showing that a little more clearly. So here we start with a congestion window of size 1. We're in the slow start state. Then there's, say, a triple duplicate ACK or a timeout. We set the congestion window to be size 1 again, but we have a slow start threshold here, which is half of this value, right? So if this is x over 2. So we do exponential growth again until we reach this point, at which point now we're in congestion avoidance. Linear increase. Now here we have a timeout. The window size is staying stable. Boom, drop down to congestion window size 1 again. Slow start, congestion avoidance, timeout, etc. So we see this behavior of whenever we have a triple duplicate ACK or a timeout, we end up reducing the congestion window to a size 1, going through slow start, and then entering congestion avoidance. So TCP Reno generally behaves similar to TCP Tahoe, with one exception, which is that on a timeout it behaves the same way, that it sets this congestion window to be size 1 and does slow start again. The assumption here is, hey, things have gone very wrong if I have a timeout. And so I'm just going to assume nothing about the network and pretend as if things were just starting from the beginning. What TCP Reno does differently is on a triple duplicate ACK, it assumes, look, a segment was lost, but other segments are arriving. Chances are I'm close to what my speed should be. I don't need to drop my congestion window to size 1. Instead, I still set the threshold to be congestion window divided by 2, that's before, but I set my congestion window itself to congestion window divided by 2. So this is what's called fast recovery, right? Rather than entering slow start again, I just have my congestion window. Then it adds another mechanism, this is called fast retransmit, which won't wait for the timeout on a triple duplicate ACK. It says, look, I have a triple duplicate ACK. It means that that segment is really likely to be lost, so I'm just going to retransmit immediately. And what this behavior means is that on a triple duplicate ACK, TCP Reno will stay in the congestion avoidance state. It isn't going to require a logarithmic number of steps to enter that state, which means the window size is bigger. Fast retransmit means it's not going to have to wait for a timeout. And so in theory, the idea is that it's not going to have a couple of round trip times where it's then ramping up, and so its overall throughput will be higher. And so this is a picture showing how TCP Reno behaves under similar circumstances. Where here we see we start in the slow start state. Here's slow start. Then we have a triple duplicate ACK. And rather than drop down to a congestion window of size 1, it sets, if our congestion window here was x, it sets the congestion window to be x divided by 2. And since that is the slow start threshold, this causes the protocol to enter congestion avoidance. Then here we see a triple duplicate ACK. Do the fast retransmit, we get the acknowledgement, we're growing the window again. Then here we have a timeout, and on a timeout, TCP Reno behaves in the same way, in that it says something has gone drastically wrong. I set my congestion window to be 1, and enter the slow start state again. So here we have slow start, congestion avoidance, timeout, and triple duplicate ACK. So this is how TCP Reno behaves. So let's walk through that. So my sender sends packet 1. I get an acknowledgement 1. I send 2 and 3. I get acknowledgements 2 and 3. I then send 4, 5, 6, 7. And let's say that packet 4 is lost. Well, the receiver is still going to send acknowledgements, but in response to 5, 6, and 7, it's going to send ACK3, 3 times. So triple duplicate ACK. So at this point, my congestion window was 1, here it was 2, here it was 4. Now, in receiving this triple duplicate ACK, TCP Reno is going to set its congestion window to be 2, immediately retransmit packet 4, right? Fast retransmit. So here's the fast retransmit, no timeout. And hopefully we will get an ACK7, at which point now we have a congestion window of size 2, and we'll send packets 8 and 9. So TCP Reno significantly improves TCP's throughput because you don't have to enter the slow start state and drop your congestion window to size 1 just when a single segment is lost. TCP NewReno improves things even a little bit more. Essentially, it behaves the same as Tahoe and Reno on timeout. When you're in the fast recovery state, it does something a little fancy with your congestion window. When you enter fast recovery, so this is when there's a triple duplicate ACK, on every duplicate ACK that you receive, you inflate the congestion window by the maximum segment size. Then when the last packet that's outstanding is acknowledged, you return to the congestion avoidance state, you set your congestion window back to the value set when entering fast recovery. And essentially what this is going to do is, if I have a large window of outstanding packets, like say, I have a very large window. In this case, let's just say, let's say I have 8 packets. It's not a super large window, but it's, for drawing, it's reasonable. And this packet here is lost, right? So let's call this packet X, right? So this packet is lost. Each of these packets are going to trigger duplicate acknowledgements. And as now TCP NewReno receives these duplicate acknowledgements, it's going to start inflating its congestion window size. And as it inflates the congestion window size, what that's going to let it do is start sending new packets. The idea here is we have evidence that packets are leaving the network. And so it's okay to send new packets. We don't want to send them too quickly because clearly we're close to the congestion point of the network. But otherwise, what happens when we do a fast retransmit, we essentially have to wait for an entire RTT before we can send a new packet. We have to do this retransmission, and then when we get the acknowledgement, we can now move the window forward. And so there's this whole RTT where essentially TCP sits idle. And you see that in this example here, where, gosh, we have this situation where there are these idle periods waiting for the retransmission. And so essentially what this tweak, which I'll sort of walk through explicitly in a second, allows TCP NewReno to do is to start sending out new packets while the fast retransmit is in flight. It starts inflating the congestion window to be bigger so that even though this was the last acknowledged packet, it can start sending new packets. But then once we get a proper acknowledgement, like let's say we get an acknowledgement for this segment here, then it suddenly reduces the congestion window size to the right size, so it's not like we've suddenly saturated the network. So let's walk through what this looks like. So let's say we have a congestion window of size 16, and we encounter a triple duplicate ACK. So the rules mean we're going to set the congestion window to be 8. So at this point, we have a triple duplicate ACK. The congestion window becomes 8. And we're going to do fast retransmit. And so a triple duplicate ACK comes in, and we send out fast retransmit. Meanwhile, while that fast retransmit packet is outstanding, we're receiving additional acknowledgments. Right? The window size was 16, and so we had a triple duplicate ACK. Essentially, we expect to receive order 16 or 15 duplicate ACKs. And so as those start streaming in, what we're going to do is increase the congestion window by 1 for each. And so we can count those 3 triple duplicate. So over this interval here, the congestion window is going to increase +1 for each of those duplicate acknowledgments, right? Which means it's going to increase up to 23. So this might seem really big. Suddenly we've inflated our congestion window from 16 to 23. But think about what this means in terms of the sequence number space. So we had this window of packets, right? And this was the last acknowledged packet here. Let's just call it packet 1, right? Then we've started, and we have an outstanding window of size 16, right? So we can send from 1, right? So we can safely send from packet 1 to 16. So when we got that last acknowledgement for 1, we could send 16. Everything is, so when 1 was acknowledged, it allowed us to send 17, so everything is good. Now we have a triple duplicate ACK, and we're not going to be able to send anything past 17 until the congestion window grows beyond 17. And so it's starting at 1, and the congestion window has shrunk to 8. And so this means that the valid packets we're allowed to send are 2, 3, 4, 5, 6, 7, 8, and 9, right? That's not very helpful. And so now, as these additional acknowledgments come in, we're going to start inflating this. So we're going to allow ourselves to send to 10, to 11, to 12, to 13, to 14, et cetera, et cetera, et cetera, until when we get, say, the 8th duplicate acknowledgement, now suddenly we have increased our congestion window size back up to 16, which means that, we could resend 17. And then when we get the 9th, we've increased it to 17, which means that we can now send packet 18. And so this will then increase up to 23. And essentially what this does is it inflates the congestion window so we can send up to packet 24. Now if you look at this carefully, packets 17, 18, 19, 20, 21, 22, 23, 24, that's 8 packets, which is equal to what the actual congestion window size is. And so the idea is that by inflating in this way, given that we halved it and now we're adding +1, the last half of acknowledgments that arrive will allow us to clock out new packets. And so essentially, then, and as soon as the fast retransmit acknowledgement comes in, we just reset everything. Gosh, things are acknowledged. Our congestion window is size 8. We can start moving forward. But essentially what this does is this inflating of the window after a triple duplicate acknowledgement allows TCP NewReno to continue to send data while the fast retransmit is in flight. And the amount of data it's going to send is equal to, and it's clocked by, again, acknowledgements coming in, so packets are leaving the network, the expected congestion window size for the next round trip time, assuming that the fast retransmitted packet is delivered successfully. So that's TCP Reno and NewReno. NewReno is generally used in many systems today, or at least the basis for TCP today. I'll talk a little bit more about more advanced TCP that deals with some modern network considerations. But on a Linux system or on Windows systems, Mac OS systems, the basic TCP algorithm that's running is very, very similar to NewReno. It turns out that congestion control is a really hard problem, and it's one of the hardest problems to build a robust network system. The basic approach that you see that has been adopted, and which seems very, very powerful and very robust, is this idea of additive increase, multiplicative decrease, that you increase a window additively, right, but then reduce it multiplicatively. So you respond very quickly when things go badly and carefully increase it. And so the trick is that when you're doing this is how to keep the pipe full and improve throughput. So there's things like fast retransmit, don't wait for a timeout, just send resend quickly. And also things like congestion window inflation, where gosh, I don't want to waste a whole round trip time waiting for the fast retransmit acknowledgement. I know stuff's leaving the network, I'm going to start sending out some new packets. I'm allowed these packets have left the network.